Hello everyone, today's lecture is on atomic structure and composition. Let's look at the objectives for today. At the end of this lesson, students should be able to answer questions about the relative mass of electrons, protons, and neutrons, the electrical charge of electrons, protons, and neutrons, composition of the nucleus and atomic mass. Students should also be able to explain what N, Z, and A stand for in the standard symbol for an atom. Students will learn the definitions of isotope, isotone, isobar, and isomer. Students will know what it means for an atom to be radioactive. We shall also define the properties of alpha, beta minus, beta plus, gamma, and X-ray radiation, and compare the penetrating ability of alpha particles, beta particles, neutrons, and gamma radiation. Let's start with the structure of the atom. Atoms are made up of protons, neutrons, and electrons. When there is an equal number of electrons and protons, the atom is electrically neutral. Electrons are negatively charged, protons are positively charged, and neutrons have no charge, so they are neutral. The structure of the atom was originally described by the classical models of Thomson, Rutherford, and Bohr. The earliest attempt to describe the structure of the atom started with the plum pudding model of Thomson. After Rutherford's experiments showed a dense nuclear core, Bohr advanced the solar system model. This was a model where electrons circle around the nucleus in stable, discrete circular orbits, and these orbits have discrete energy levels or electron shells. A few years later, research by Sommerfeld, Pauli, as well as de Broglie later led to the quantum mechanical model proposed by Heisenberg, Born, and Schrödinger. In this lecture, we shall focus on Bohr's classical model. In Bohr's model of the atom, electrons exist in discrete, stable orbitals called energy levels. Traditional names of these energy levels or orbitals were derived from X-ray notation, where the first orbital was called the K shell and the second orbital the L shell, and so on. Each shell was also given numbers, with the K shell having the number 1 and other numbers as shown in the figure. The closest shell to the nucleus is the K shell. Each shell or orbital is made up of subshells labeled S, P, D, F, and more. The subshells are based on observations of spectroscopic lines of alkali elements. The appearance of the spectroscopic lines are described by words like sharp, principal, diffuse, and fundamental. The first letter in each word is the basis for the letters S, P, D, and F that were used to describe suborbitals. The maximum number of electrons per shell is given by the formula 2n squared. So the K shell with n equals 1, there are a maximum of 2 electrons. In the L shell with n equals 2, there are 8 electrons, and the figure shows the shells with the maximum number of electrons in each shell. Because Bohr's model tells us that the electrons are in discrete stable orbits, we can say the electrons are bound in those orbits. The binding energy is the energy needed to remove an electron from an atom's shell or orbit. The energy needed to remove an electron must equal or exceed the binding energy of the electron in the shell or orbit. Because the K shell is closer to the nucleus, the K shell has a stronger binding energy than other shells. Also, binding energy increases as the number of protons in the nucleus increases. This is seen by comparing the binding energies of the K shell in hydrogen and the binding energies of tungsten as shown in this figure. So in this figure, you can see that the K shell of hydrogen has a binding energy of negative 13.5 electron volts. The K shell of tungsten has a binding energy of negative 69,500 electron volts. Electrons in discrete orbits can make transitions from one energy level to another. There is a transition energy, which is the difference in binding energy between the energy levels involved. For example, the formula is shown here where the binding energy for the transition between a K shell and an L shell is given by the difference in energy between the K shell and the L shell. Once electrons transition between energy levels, there is a release of energy in the form of X-ray radiation. The radiation is called a characteristic X-ray radiation because it is unique to the atom involved. Its energy is the difference between the vacant shell energy and the transition shell energy. Transitions between adjacent shells is labeled with alpha, and transitions of non-adjacent shells are labeled with beta. On this slide, we have a K characteristic X-ray energy formula spelled out. because it represents the transition between a vacant K shell and an L shell. It will also be labeled an alpha transition because it occurs between the adjacent L shell and the K shell. Auger electrons are those electrons produced when the energy of a transition electron is transferred directly to an orbital electron, usually in the same shell as the transitioning electron, leading to the release of an Auger electron. Again, the Auger electron energy is the difference between the transition energy and the binding energy of the ejected electron. So this figure shows you an electron making a transition from an M shell to a vacant shell. In this case, the energy of the electron is transferred directly to an orbital electron, which is then knocked out of the M shell. Now let's look at some size comparisons. Neutrons were initially thought to have approximately the same size as protons, but no electrical charge. It was later found out a neutron is slightly heavier than a proton. The ratio of their masses is 1840 to 1836. Electrons are lighter than neutrons and protons. An electron is about 1/1800 times smaller than a proton. Once large numbers of elements were identified and classified, a way was needed to present them in an orderly and consistent fashion. The periodic table is a way to place the elements in groups based on various properties like atom size, electron affinity, ionization energy, and so on. The current periodic table is a Mendeleev table named after the Russian chemist Dmitry Mendeleev. On this table, elements are placed in groups and grow larger as we go down the group. Additional trends are shown on the figures on the slide. There are 92 naturally occurring elements on Earth. If you include neptunium and plutonium, then you have 94. Elements with atomic number larger than 83 are naturally unstable. These 92 naturally occurring elements have a total of 339 isotopes. Of these, 286 isotopes are stable. The remaining are unstable. We shall later see that unstable isotopes of an element decay to a more stable state by a process called radioactive decay. For example, carbon-14 is an unstable or radioactive isotope of carbon-12. There is a standard nomenclature for writing the symbol of an atom. It is shown on this slide, where N is equal to the number of neutrons, Z is the number of protons, and A is the mass number, which is the number of protons plus number of neutrons. Take the element helium for example. Helium has 2 protons and 2 neutrons, so its mass number is 2 plus 2 or 4. So we can write a symbol for helium as shown, where we have the 2 neutrons, 2 protons, and a mass number of 4. We can see the second example of the element carbon shown. An atom having 6 neutrons, 6 protons, and a mass number of 12 is called carbon. You can have a variation of carbon where you have 8 neutrons, 6 protons, and that element is called carbon-14. An example of an unstable element is cobalt-57, a common radionuclide used in nuclear medicine, and also cobalt-60. Both cobalts have the same number of protons, which is 27, but cobalt-57 has 30 neutrons and cobalt-60 has 33 neutrons. So the mass number of cobalt-57 is 57 and the mass number of cobalt-60 is 60. In the last few slides, we looked at examples of elements and how to write them using the standard nomenclature that lists the number of neutrons, number of protons, and mass numbers. On this slide, we can classify elements based on the number of neutrons, number of protons, and mass number, as well as their energy state. There are 4 classifications. We shall start with isotopes. Isotopes are elements with the same atomic numbers but different mass numbers. For example, cobalt-57 and cobalt-60 are isotopes. They have the same number of protons, which is 27, but different mass numbers. The next is isotones. These are elements having the same number of neutrons. For example, we have iodine-131 and xenon-132. They have the same number of neutrons, which is 78, but they have different numbers of protons. Isobars are elements with the same mass numbers. For example, molybdenum-99 and technetium-99 are isobars because they have the same mass number. Finally, we have isomers. These are elements having the same atomic numbers, neutron numbers, and mass numbers but have different energy levels. For example, technetium-99 and technetium-99m are isomers. Technetium-99m is a metastable state of technetium-99. This table summarizes the classifications of nuclear families. The bold letters in each term provides a convenient way to remember the definitions of each of those terms. Certain combinations of neutrons and protons are unstable. Instability is determined by the neutron to proton ratios of the elements. When the neutron to proton ratio is different from 1, the atom will be unstable. So neutron excess and proton excess or neutron deficiency both lead to instability. Unstable nuclei would decay to a different, more stable nuclei and emit radiation in the form of alpha particles, beta particles, or gamma rays in the process. The chart shows the line of stability and the division between proton-rich and neutron-rich elements. The neutron to proton ratio is close to 1 for the low Z elements and increases to about 1.5 for heavier elements. Elements further from the line of stability are more unstable and the half-life is shorter for those elements. Elements above the line of stability are neutron-rich and elements below the line of stability are proton-rich. While we can classify elements as stable or unstable because of the neutron to proton ratios, whether there is an even or odd number of protons or neutrons is also significant. This table shows the number of stable nuclides based on whether there is an even or odd number of protons and neutrons. It turns out an even number of protons and neutrons is good for stability, while an odd number likely means the element is unstable. In between that, having a mixture of even and odd numbers means the elements can have a nuclear magnetic resonance signal. We shall talk about nuclear magnetic resonance in a different lecture. This second table shows elements with a net magnetic moment. These elements can be used for nuclear magnetic resonance spectroscopy. Because unstable nuclei decay until they reach a more stable energy state, we can talk of the higher energy unstable element as the parent nuclei and the lower energy nuclei that results from the decay of the parent as the daughter nuclide. The daughter may be stable or unstable. If it's unstable, it will also decay to a lower energy level. This process of decay will continue until a stable state is reached. For heavy elements like uranium-238, the end result of this continuous decay is the element lead. An unstable nuclear is said to be radioactive. Radioactivity is the spontaneous disintegration of atomic nuclei accompanied by the emission of small particles and energy. Depending on the type of emission, scientists define the disintegration as alpha decay, beta or positron decay, and gamma radiation, where gamma radiation is a short wavelength electromagnetic wave. We shall learn more about these types of radioactive particles shortly. Because radioactivity is from the nucleus, let's take a closer look at the nucleus. The nucleus is made up of protons and neutrons, collectively called nucleons. When we look at the structure of the nucleus, we see that nucleons are held together by two forces. The electrostatic force, which is based on the Coulomb's law, is a repulsive force between the positively charged protons. The second force is the nuclear force that counteracts the electrostatic Coulomb forces. It causes the attraction between the nucleons. This force is stronger than the Coulomb repulsive forces that will otherwise split the nucleus apart. The energy released in a configuration transformation or decay is emitted in the form of either photons or particulate radiation. An accepted model of the nucleus is the shell model. In the shell model, nucleons move about in orbits much like in the Bohr model. Also, nucleons exist in specific configurations in the nucleus like in the Bohr model. There are several nuclear configurations. Some of these nuclear configurations are more stable than others. Depending on the stability of a configuration, the state of a nucleus can be classified as a ground state. The ground states are stable except in the case of radioactive nuclides, where even ground states are unstable. Another classification is the excited states. These are unstable arrangements. Nuclei in these states transform or decay to a more stable state in a short time, in a time as short as 10 picoseconds. A final configuration is the metastable states. These are also unstable but have longer durations or lifespans than excited states. The nuclear binding energy is the energy needed to separate the nucleus into its components. Total energy of bound particles is less than the total energy of separated constituents. Because mass is equivalent to energy according to Einstein's equation E equals mc squared, we will also see that atomic mass is less than the sum of the individual masses of component particles. The difference in mass between the sum of individual protons, neutrons, and electrons of an atom and its atomic mass is called a mass defect. This mass defect shows that a large amount of energy can be released when the nucleus is broken into its component parts of electrons, protons, and neutrons. We can take the idea of binding energy a bit further by observing that the total binding energy of the nucleus may be divided by the mass number A to obtain the average binding energy per nucleon. A plot of the binding energy per nucleon versus the mass number is shown here for most elements. This plot shows areas where there are elements that can undergo fusion, as well as elements that can fission. We will talk more about fission elements in the nuclear medicine lecture at a later date. So elements on this side can undergo fission, and those on the side here undergo fusion. Let's now look at what happens during radioactive decay. A heavy atom can emit alpha particles in a process called alpha radiation. Alpha particles are nuclei of ordinary helium atoms, which consist of 2 protons and 2 neutrons. They have very low penetrating power in materials. They move at slower velocity than the other types of radiations. They are positively charged and can be deflected by a magnetic field. If an atom is neutron-rich, it decays by emitting a beta-minus particle. Beta-minus particles are high-speed electrons. They are more penetrating than alpha rays or alpha particles but less than photons. They can move at very high speeds and experience strong deflections in a magnetic field. They are also negatively charged. For atoms that are proton-rich, they can decay by emitting a beta-plus particle. Beta-plus particles are high-speed electrons. They are more penetrating than alpha particles but less than photons. Beta-plus particles can be deflected strongly by a magnetic field. They have the same magnitude of charge as electrons but are positive rather than negatively charged. They travel a short distance from their origin before combining with an electron in an annihilation interaction. Electron capture is an alternative to beta-plus decay for proton-rich radionuclides. The nuclide captures an orbital electron from the K or L shell and neutralizes a proton. This leads to the conversion of a proton into a neutron. There are 2 possible secondary events after electron capture. There is the emission of a characteristic X-ray or isomeric transition. In characteristic X-ray radiation, an electron drops from an outer electron shell to fill the vacant inner shell. The energy difference leads to an X-ray photon being released, which is equal to the difference in binding energy of the 2 electron shells involved in the transition. We shall discuss isomeric transition on the next slide. A lot of the decay processes we mentioned can result in an atom being in an excited state. In this state, the atom is unstable and has excess energy. That energy is released in the form of a gamma radiation. The atom is said to be in a metastable state, and the transition to a more stable state is called isomeric transition, particularly when the atom does not change itself, but only the energy level changes. An example is the technetium-99m, which is a metastable state of technetium-99. The difference in energy level is 140 keV. An alternative to isomeric transition is internal conversion. The nucleus decays by transferring gamma ray energy to an orbital electron, which is then ejected. The result is a process where outer electrons again fill the inner vacant shell, and these transitions can result in characteristic X-rays or Auger electrons as described previously. The electron is called a conversion electron. Its energy is the difference in gamma ray energy and binding energy of the shell the electron is ejected from. Let's end by comparing the penetrating ability of various radiations. The least penetrating radiations are alpha particles, which are heavy charged particles, followed by beta particles, which are charged particles but not as heavy as alpha particles. Gamma rays are more penetrating than beta particles, and neutrons are the most penetrating radiations. Neutrons are heavy particles but are neutral with no charge. Let's finish up by answering a few review questions. First question: what is the atomic mass A of atoms with 2 protons, 2 neutrons, and 4 electrons? If your answer was C, that would be correct. Atomic mass or mass number is the sum of protons and neutrons, so that will be 4. Next question: the charge of an electron is, and you have a few choices. Negative is the first choice, positive is the second, and neutral is the third choice. The correct answer for the charge of an electron is negative. Third question. In the standard symbol for an atom, the letter Z stands for the number of, and your choices are A, protons, B, neutrons, C, protons plus neutrons, D, electrons, or E, protons plus electrons. The correct answer is A, protons. The letter Z stands for the number of protons, and that is the same as atomic number. Next question. Energy that has come out of a sample of radioactive atoms has no mass. What type of radiation is it most likely to be? The choices are A, beta minus particle, B, beta plus particle, C, an alpha particle, or D, a gamma ray. The correct answer is D, a gamma ray. Next question. A sample of two atoms are grouped as shown. We have the molybdenum with a mass number of 98 and technetium with a mass number of 99. They are considered to be what? The choices are A, isotopes, B, isotones, C, isobars, and D, isomers. The correct answer is B, isotones. So this is the last question and this is the last slide. So thank you for watching this presentation.